Welcome back. The objective of this video is to continue to become proficient using our calculator and creating a logarithmic regression model. This problem was going to have a little twist to it though because of our dependent and independent variables. In example 10, it says a university study on sleep related to caffeine drinks is shown in the table below. Participants were given 250 milligrams of caffeine in their bloodstream. The caffeine level was measured at various times. So we're going to determine the equation for a logarithmic regression function for the data representing time as a function of caffeine levels. So in this situation, our caffeine levels are independent variable, those are our x's, and time is dependent, our y. So this is one of the few times that we'll use time as y. Usually time is x, but in this case, time is going to be our y's. So we've got our table here with our data, and we'll go ahead and enter that data into list 1 and list 2 in our calculator, and then we'll find the logarithmic equation. All right, so now I have my calculator set correctly on my screen here for you, so you can see what's going on. So we'll just go into the Stat menu, Edit. We'll edit list 1 and list 2. So we'll put our data in list 1. I've done that already, and list 2. And once that's complete and correct, then we can go ahead and head back to the Stat menu, Calc, and we're going to do a linear regression, which is option 9. We're going to grab from list 1 and list 2, and we're going to store our regression equation using alpha F4, and we'll store it in Y1. And then we'll go ahead and calculate our linear regression. And we get an A value of 40.800 or 01 and a B value of negative 7.214. And that's automatically saved in my y equals. So we'll go ahead and write that down on our notes, and then we'll take a look at some more of the questions. So we have that written down. And then it asks, find the time it takes for an average person to metabolize 50% of the caffeine in their bloodstream. So 50%. 50% of what? Well, that would be 50% of the 250 that they were given to start with. So we're asked to find an x of 125. So half of 250 is 125. So we want to find f of 125. So we put that into our calculator, and it'll crank out an answer for us. So zipping back to my calculator, based on my data, I set my window from negative 25 to 300. I counted by 25s. My y, minimum y, was negative 5 I'm going to use, and my maximum y is going to be 15. I'll count by ones, and I'll just use the value key. So second calc value, we'll substitute 125 into the function. Apparently it's graphing it for me already, and we get 5.9698 or 5.970 hours. So we can say by putting 125 into our function that it'll take 5.970 hours to metabolize 50% of the caffeine. In C, it says Avery drank an energy drink containing 250 milligrams of caffeine at 9 a.m. How much caffeine will be in his bloodstream 10 hours later? So now remember, 10 is a y. 10 equals 40.808 minus 7.214 natural log of x. So what we want to find, we want to solve for x. There's a couple ways to do this. I'm just going to go ahead and use the calculator, and I'm going to find the intersection between y equals 10 and our function. So our function was stored in y1. It's listed there. and then I've got y3. I'll do y equals 10, and we'll go ahead and graph that, and then we just need to find the intersection. So second, calc, option 5 is intersect, enter, 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 3 enters, and it gets us 71.497 is the answer. So he'll have about 71.5 milligrams of caffeine after 10 hours. So there you go, 71.497 milligrams of caffeine after 10 hours. D says the study found a majority of participants were able to sleep when their caffeine levels fell below 70 milligrams. Find the time to the nearest hour for the body to metabolize the caffeine to reach 70 milligrams. So again, we want to find the time, so we want to find the y. So in this case, we're just going to do f of 70. So again, I can use the value key on my calculator and do x equals 70 and input that in, and we will get an answer of about 10.152. Let's see how that looks. Second calc value, x is 70, and sure enough, we get 10.152, 10.153. So putting that into our function, showing that we're doing that, and we get an answer of 10.152. So E says, use the regression equation, find the x-intercept to the nearest tenth, explain the meaning of the x-intercept in the context of this sleep study. So time is our y. We want y to be 0. That's our x-intercept. Our x-intercept is some x where y is 0 and y is time. So this represents the caffeine level. This is the caffeine level. Make sure I spell caffeine correctly. At time 0. And I can find that by graphing y equals 0 in my calculator and then finding the intersection there. So I can graph those two, and that's the intersection of magenta and the blue. And second calc, intersect, enter, 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 and we get about 200, almost 286, 285.963. 285.963 milligrams. Example 11 says the wind speed s in miles per hour near the center of our tornado is related to the distance d in miles that the tornado travels, given the equation s of d equals 93 log d plus 65. A tornado whose wind speed was 220 miles per hour struck a town in Nebraska. How far did the tornado travel? So we have the wind speed of 220 miles per hour. Well, this is a y value. This is an output. And so we want to find x when we have a y of 220. So using our function, we can say 220 equals 93 log base 10 of d, log d plus 65. We can subtract 65 from both sides, and we get 155 equals 93 log d. Divide both sides by 93. Both of these are multiples of 3, and it simplifies to 5/3 equals log d. So we've got log base 10 of d. I need to solve for d. I'm going to convert to exponential form. So we have 10 to the 5/3 equals d. And we put 10 to the 5/3 in our calculator and get 46.416 miles equals d. In example 12, Mr. Craig gave his students a poster of math properties. They studied the image for 90 seconds. Beginning 1 day later, a quiz was given each day to test their memory of the poster. The table below represents the average score for each day. So I'm going to create two lists. I've used list 1 and list 2, so I'm going to use list 3 and list 4 in my calculator. Input my days and my score into my graphing calculator. So we'll go Stat, Edit. I'll cruise over to list 3 and list 4. I've got my data entered, and now I can go figure out my regression. We'll go Stat, Calc, and we want to do a natural log regression, which is option 9. And I'm going to use list 3, so I got to change my lists. List 3, and second L4, list 4, and I'll store my equation in Y2, so alpha F4, we'll store it in Y2, and we'll calculate our regression. So my B value is, my A value is 76.070, my B value is negative 7.88. I'll go ahead and write that in my notes, and it is also stored here in Y2. I'll get rid of my values for Y4. So I'll call my function P of x equals 76.070 minus 7.882 natural log of x. Then use your model to predict the average test score after 14 days. We have some options here. We could do our table and table set with our function. We could do value. So we just need to find P of 14 equals 76.070 minus 7.882 natural log of 14. In fact, we could just type this into our calculator as well and get that. And when we do, we get a value of 55.27. So we would expect after 14 days, there would be down to about 55.27% would be their score. And that wraps up this particular video, a little disjointed with two different venues, but we'll get some practice with problems like this when I see you in class.